Hey everyone, good evening. So today we have Dr. Dishant Pandya with us for the Mentor Speak session. So Dr. Dishant Pandya has done his PhD from the Maharaja Sayajirao University, Baroda, in the field of general relativity on the solution of Einstein's field equation and created a large class describing the compact stars. He has over 16 years of experience. He has published several research articles and written 3 book chapters. Currently, Dr. Dishant researches theoretical astrophysics, applied mathematics, image processing, geometry. His recent publication is FINCH's key solution of anisotropic stellar models in F of R gravity. So we are very happy to have you, Dishant sir, with us. So hi everyone, good evening. We'll begin the session now.
Thank you very much, Sagar. And I first of all wishing you all the best to all the research aspirants here. Uh, First of all, let me really thank you, Sagar, because I have seen your lecture as well, and you have covered very nicely the special theory of relativity. So many of the students might have obtained a good platform to start with theoretical astrophysics. And the first step that you all have taken here, that is started with special theory of relativity. These are the fundamental concepts that we require while dealing with research. So in today's talk, I will give you briefly a glimpse of the research work and how we can carry out the research work in the field of general theory of relativity and especially towards the neutron stars. Okay, so let's begin our journey with the first part, that is called general theory of relativity. Uh, we all are familiar with the basic concept of special theory of relativity and how general theory of relativity evolved. Okay, mainly there are two postulates that come across when you start studying general theory of relativity. The first one is principle of equivalence, which states that the gravitational field produced by the attraction of masses is same as the accelerating frame of reference in the neighborhood of any point. That is a principle of equivalence. The second one is principle of general covariance, which states that the laws of physics must be same in the all in the all coordinate system. So basically, we will consider here general reference frames, and that is the reason that we require the knowledge of tensors. Okay, so you might have seen the postulates of special theory of relativity where we were using inertial frame of reference, right? But here we will have any kind of general frame of reference, and that is the reason that once you consider any rule which basically gives you the same footing in either of the coordinate system, which basically described by tensors. So that is the reason we need to understand tensor calculus as well. Fine. Next one is our main target is to basically create mathematical model which suggests the physics of neutrons. So Einstein first fused space and time together for the description of four-dimensional entity, which is called space-time. This distance between two events is given by Riemannian metric given by equation number 1. ds square is equal to gij dxi dx. Okay, so you might be familiar with this one. Okay, this entity, and Sagar has also introduced you towards the four vectors, and based upon that notion, you can have an idea of distance between two vectors. So once you go with this, you will have the metric defined by equation number 1. Here, these metric coefficients Gij, and they are functions of the space-time coordinates. Space-time coordinates means you have x, y, and z, and t as well, right? Sorry, t. Okay, so these are the coordinates that we are talking about. Now we will consider the signature with plus, minus, 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 this sign. Okay, so this is our sign convention, right? And this sign convention we will throughout follow in our research. So either of these sign convention can be followed. Okay, or either you go with minus, plus, 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 right? Or you can go with plus, minus, minus, minus. Okay, now when you consider the matter, at that time Einstein's field equations have this representation: Rij minus 1/2 Rgij is equal to minus 8 pi g upon c square Tij. So these are the components. Rich is scalar, okay, rich is vector, tensor, and this is Gij, that is metric coefficients. Okay, this is universal gravitational constant, speed of light, and energy momentum tensor. So these are the factors that will come into picture when we say that we are discussing Einstein's field equations. Okay, later on we will see that what will be the significance of these Einstein's field equations in our research. Okay, so as I told you, Rij is Ricci tensor, R is Ricci scalar, Tij are components of energy momentum tensor describing the physical content of the space-time. Now Rij and R has these expressions. Okay, when you study general theory of relativity theoretically, you will have these expressions, okay, where Rij basically is given by this a little bit lengthy expression where gamma Kij is nothing but Christoffel symbol of second kind. So once you start studying the theory, you will study Christoffel symbols of first kind, okay, as well as second kind. Second kind is given by this definition, okay. And of course, at that time, you will also learn the relation of these dummy suffixes. Okay. So gamma Kij is equal to 1 of GKL. This L can be nullified with these lower suffixes. You can see here the cyclicity of these metric coefficients along with their indices. Okay. So these are given by Christoffel, and hence the name Christoffel symbols of first kind and second kind. So based upon this, once again, if you try to contract this Ricci tensor, you will get R is equal to Gij Rij, and that is nothing but Ricci scale. Okay. Now the most general spherically symmetric space-time, if you see, that can be given by this equation number 6. So this is very important. We have basically converted our XYZ T into spherical polar coordinate system. So this is ds square e raised to nu dt square minus e raised to lambda dr square minus r square d theta square plus sine square theta d phi square. Okay, and here nu and lambda, they may be functions of r and t. So this is the most general spherical symmetric space-time metric, okay, for the 4-dimensional space. Later on, once you consider a special case, you can have this t overrule, and you can simply consider nu as a function of r and lambda as a function of r. This is just for the sake of convenience, for the sake of considering only one dimension. Okay, so that is the reason that we will be starting with one dimension, and then we can extend the notion for higher dimensions. Okay, then let's see some background of neutron stars, because this was the basic thing we required space-time metric, and then now we will be in a position to first of all understand the objects on which we are trying to apply our knowledge. Okay, in 1931, as you can see here, Chandrasekhar gave that limit called Chandrasekhar limit, 1.4 solar mass. If you have the mass which is greater than this 1.4 solar mass, then there will be no star which can be in a state of hydrostatic equilibrium. It means this is the maximum limit that any star can achieve for the hydrostatic equilibrium. When the thermonuclear energy in a star is exhausted, the star loses its hydrostatic equilibrium and undergo a contraction that can be halted when it reaches a new state of equilibrium depending upon its mass. Now, again, mass plays a vital role here. Depending upon the mass of that star, you will have a few categorization here. Just you can see here in the last line, you will have, based upon the remnant of this collapsing star, either you will have white dwarf or neutron star or a black hole. Okay. Now, what are the white dwarfs? In simple language, if you want to see, then it is nothing but it has an equilibrium which basically counterbalances gravitational force by its electron degeneracy pressure. So that state, in physics, you can say that this state will be produced by white dwarfs. For neutron stars, this gravitational collapse is basically avoided due to the repulsive neutron degeneracy pressure. And when the mass of star exceeds approximately 3 solar masses, then no force is sufficient to keep this equilibrium. And hence, the ultimate fate of such a massive star is a black hole. Okay. Now, basically, we have a very good category to study stars, and that category has a big name called compact stars. Now, there are few properties which basically identifies that you are now studying compact stars. Okay, the first property here is hydrostatic equilibrium is attained by respective particle degeneracy pressure. Then second property is the radius of such stars will be in the range, maybe minimum less around, you can say 8, 9 or 10 kilometers, and maximum you can say 5,000 kilometers. So even if you consider the largest radius of such stars, it will be having the radius which is less than the Earth's radius. You can say Earth's radius is 6,371 kilometers, but the maximum star, the largest star in this category, in compact stars, might have the radius around 5,000 kilometers. So that is the largest star. And usually we are just going with the lower bound, that is 10 to 12 kilometers in radius. Next is for those stars who are having the radius maybe nearly 5,000 kilometers, they have density around 10 to the power 6 grams per centimeter cube. And the stars with lower radius around 10 to 12 kilometers, they will have densities around 10 to the power 15 grams per centimeter cube. Okay, you can compare this density with Earth's density. Earth's density is nearly 5.5, or you can say 6 grams per centimeter cube approximately, whereas the substance in such stars has density 10 to the power 15 grams. You can say, you can see here a clear difference, and you can say the higher amount of density in such stars. You can say, and that is the reason that many of the things even today we don't know about such stars. And the fourth property is mass is nearly 1 solar mass. 1 solar mass, that is 2 into 10 to the power 30 kilogram. Now Earth's mass is, you can see here, 5.972 into 10 to the power 24 kg. And now you just add 6 more digits in order to get 1 solar mass. And we are talking about larger solar masses here, maybe 1 to 3, in a range of 1 to 3 solar masses. And hence, the mass of white dwarf is nearly 3,32,946 times that of the mass of Earth. Now see, this is the, you can say, the difference between such stars and the existing entities on Earth. Okay, right now we are on Earth, and we basically try to understand this connection with the Earth so that we can at least visualize that how much dense such stars are. Okay, so compact stars are basically some strange stars excluding black holes. Okay, right now just keep aside black holes and think about strange stars. Why we are calling this as strange stars? Because of this reason. Jotania and Tikaker in 2006, they have extensively studied such class of compact stars, and finally they arrived here by two types, okay, strange star with the classification on the basis of compactification parameter. Now see, when you start studying any research paper, you might come across this terminology called compactification parameter. So compactification parameter U is given by this ratio, mass to the radius of the star. So if this ratio is greater than 0.3, then it is called type 1. And if that ratio is in between 0.2 to 0.3, then it is called type 2. Okay. So this is basic category of strange star. So you can immediately calculate once you have the basic information about the mass and the radius of that particular star. Okay. Okay. Now this was second aspect that we have covered so far. Now coming to the third phase of our research direction. That phase is you need to understand, or you need to have a proper knowledge of energy momentum tensor. So first we will see here energy momentum tensor for perfect fluid. A perfect fluid means there is no shear stress and there is no anisotropy and no viscosity. So in this case, if you study energy momentum tensor, then it can be given by this expression number 7. Okay, and this is our base, because on the basis of this you can always construct your theory in order to accumulate few more parameters. For example, just after a few slides we will see that how anisotropy can be modified here. Okay, it can be covered here in the modified expression of perfect fluid. So this is the first thing. Now why people are studying anisotropicity? Because isotropy is there, but in anisotropy, in you can say in 1972, the first time Ruderman and then Canuto and Bowers and Liang in 1974, they have reported that in high density region there must be anisotropy, and hence it would be more realistic if you study anisotropic fluid distributions rather to study perfect fluids, because perfect fluid is, you can say in a simple language, it's nothing but an ideal fluid. So whatever the theories you are making, whatever the models you are creating, that will have a very less impact in the realistic situations. Okay, now why there is an anisotropy? Because they basically found that in a very high density, density is so much high that radial pressure and transverse pressure, they become different, and that is the reason that anisotropy evolved here. Okay, the radial pressure PR and transverse pressure or tangential pressure PT or P per, they are different from each other, and hence now we need to take into account anisotropy. Maharaj and Martens in 1989, you can see the difference here. Even to devise such Einstein's field equations and the energy momentum tensor equivalently for anisotropic fluid distributions, it took around 15 years. So you can say here, while discussing theories, it's really difficult to set up a proper theory with proper justification. Okay, so without any glitch, if you want to establish theory, then definitely you need to go in real depth. Okay, so once scientists have found that anisotropy is really an interesting thing to study, then such theory came into picture, and in 1989 this equation was established. Okay, it's a very good paper. Those who are interested, they can refer Maharaj and Martin's 1989 paper, and this paper basically gave this idea that we need to add here some more factor in order to settle this anisotropicity. Okay, let's coming to the previous expression. You can see here, this is Pij rho plus P Uiuj minus Pgij. But here, okay, but here you have additional term that is called pi ij. Here, rho is the proper density, P is the isotropic pressure, and UI is the 4 velocity field of the fluid. Now, what is pi ij? This pi ij basically defines your anisotropy. Anisotropic stress tensor is given by this one. Pi ij is equal to root 3 s CICJ minus 1 by 3 UIUJ minus GIJ. And basically, this is a very large calculation. Okay, based upon this lengthy calculation, they have found this expression pi ij. Now we are basically considering this expression in our research, but they have calculated in very realistic manner. Okay, they have proved this pi ij, and here this ci, this vector is nothing but a radial vector, 0 minus e to the power minus lambda to 0 0. Now this radial vector can be obtained on the basis of our considered space-time. Okay, space-time metric. Now, for a spherically symmetric anisotropic distribution, this S, capital S, is nothing but magnitude of the anisotropic stress. Okay. Now, for the space-time metric considered in equation number 6, this one, for this space-time metric. So please keep in mind, this space-time metric will be our first expression while starting our research. Okay, ds square is equal to e raised to nu dt square minus e raised to lambda dr square minus r square into bracket d theta square plus sin square theta d phi square. Okay, based upon this, now we are trying to find out the non-vanishing components of energy momentum tensor 8. That is this previous one. Okay, and what are those components? Based upon this tensor theory, if you see, T00 will be non-vanishing, T11, T22, and T33. Okay, rest all the components like T12 or T21, whatever the components you are getting out of those 16, those will be vanishing, but these 4 will be non-vanishing. Okay, and they have this format. Okay, now this is an interesting story. You have found an energy momentum tensor with non-zero components, non-vanishing components, once you consider the anisotropy. Okay, so how do you can say, how do you are relating this thing, radial pressure and transverse pressures? They have this relationship, equation number 11 and 12. PR is given by minus T11 equal to this, and P perp is equal to this. Now you just try to understand this thing, that out of these 11 and 12, you will have this equation number 13, and which is basically giving you the relationship of this radial pressure and transverse pressure. See, this is, you can say, a very minute quantity. PR and P perp are differing from a function root 3s, and you can say this root 3 is nothing but here in product. So PR minus P perp. So difference between radial pressure and transverse pressure is given by this equation number 13. And you can say that it is nothing but a magnitude of anisotropy. For a perfect fluid, this PR and P perp both are equal, and therefore anisotropy will be 0. Clear? So how you can say that while working with theory, whatever the generalized form you have found, that is correct, then ideally it should match with the starting point when you consider the difference, which is 0. In this case, radial pressure and transverse pressure, if you consider the difference of these two, which are 0, that means when radial pressure is exactly equal to the transverse pressure, then there will be no anisotropy, and that is the case here in equation 13. And therefore we can say that we have purely isotropic case, right? And hence S equal to 0 in such cases. Okay, now we have finished our third phase. What about the fourth step? Once you understood and gone through the basic theoretical aspect, now you can start with the some important metrics. Okay, now there are various metrics in this field, and you can start with any of the metrics. For example, if you consider the spheroidal space-time metric, it can be given by equation number 14 in most generalized form. where you have these three categories as well, where k is equal to 1 minus b square over r square. When k is less than 1, yeah, k is the entity which is given by this expression 1 minus b square over r square. Where k is less than 1, the metric of space coordinates is regular points for which r square is less than r square. Okay. Similarly, when k is equal to 1, the metric corresponds to the flat space time, and when k equal to 0, you have metrics which represent basically a 3 sphere. Okay. So these are the classifications of this spheroidal space-time metric. Now some of the special cases when you have k equal to 0, but along with that, if you consider e to the power nu r. Now see, I'm just making you connected that how such metrics are involved. I'm coming towards the previous expression, this one. You can observe here equation number 6, where e to the power nu or e to the power lambda, if you consider this e to the power nu expression, then you will have different metrics. So for example, in this case, yeah, e to the power nu, or if I'm considering this one, this matrix was considered by Schwarzschild, which is giving Schwarzschild interior solution. And this is one of the most famous calculations once you start studying general theory of relativity, that one should have a good idea about Schwarzschild interior solution and Schwarzschild exterior metric. Okay. When you consider nu equal to 0, your metric is nothing but Einstein's universe. And when you consider e to the power nu r is equal to 1 minus r square over r square, it gives you de Sitter's universe. So the students who are basically focusing in studying of cosmology, they may have an idea that this will be the starting point, and then you can definitely go towards the study of cosmology. Okay, where you can have a more generalized version called Robertson-Walker matrix. Okay, so I'm just giving you a brief idea that how such metrics are there, and it's not a simple task to create such metrics. So you need to follow rigorous theoretical aspects as well to establish such metrics. Okay, another type of matrix is called pseudo-spheroidal spacetime metric, and this metric is extensively studied by Thomas and Tikaker, okay, from 1991 onwards. And this metric basically has this relationship 1 plus b square over r square. So if you see the previous part, it was related to 1 minus b square over r square. But when you consider this plus part, it is nothing but a pseudo-spheroidal space-time. Here, this k greater than 1 basically describes our anisotropic fluid distributions. Okay. The third metric is called paraboloidal space-time metric. Here, you can see here that this is e to the power lambda. Okay, e to the power lambda, and which is equal to this expression. Okay. Yeah. So here, this is nothing but a paraboloidal spacetime. It represents a paraboloidal geometry, and obviously R is a geometric parameter here as well. Now, coming to the fifth phase of our research part, that is, now we are in a position to grab a suitable interior metric. Okay, then we need to now solve Einstein's field equations. Okay, so this is, you can say, basically a heart of our whole research idea, that these are the equations that we need to solve. So basically what we need to do is, we have these all functions mu and lambda, and e to the power minus lambda, e to the power nu as well. Based upon those functions, you can solve these triplets equations 18, 19 and 20, and they are basically highly non-linear second order ordinary differential equations. So we need to carry out very lengthy computation here in order to solve these equations. Maharaj and Martins have further simplified these relations and connected with the actual anisotropic expression. So these are equivalent expressions 21, 22 and 23 with the previous one. Okay, so either you study or solve these 18, 19, 20, or you can solve 21, 22 and 23. which are called Einstein's field equations for anisotropic fluid distributions. Okay, so for anisotropic fluid distributions, we have these expressions on the right hand side part, and on the left hand side we have these standard expressions. So you can see here that this is density expression, and this is radial pressure expression, this is transverse pressures expression. And once you have readily available your metric, you can always calculate these second order differential equations and all these three equations. Now you can try to solve this one. Now basically you have variables, you have more variables and less number of equations. Okay, and see, and this is okay. Once again this 21, 22 and 23 have relevant equivalent expressions 24, 25 and 26. Okay, and now you can see that these are the expressions which you can equivalently use, okay, while establishing our anisotropic relations. E to the power minus lambda is given by 1 minus 2m by r. This is standard metric. You can consider the equation number 6, and the standard metric with this relation 1 minus 2m by r. And then radial pressure can also be connected with this expression, and similarly rho, pr and p per, I mean anisotropic magnitude of anisotropic stress, that is S, is given by this. So once you are in a position, you can always solve this equation number 24, 25 and 26. Okay, here we need to note that this m, that is the mass, has this relationship. Basically we are familiar with the density and volume expression, and this is nothing but the most general way to consider the mass function, okay, in the integral form. So that was the fifth part. Now sixth part is, once you have that knowledge, you can in fact expand that one while considering the charged distributions. Okay, and for the charged distributions, you have this charged expression E square, and E square. So you can just notice here that only this minute difference is given by this E square part. Okay, so if you want to study the charged part in your considered fluid distribution, then also you have readily available expressions 28, 29 and 30. Right now we are not considering charge part, but that's just for your reference, that you can use these relations as well. Okay, now I'm just demonstrating that how I have implemented these the full model in order to establish a good working mathematical model, which is basically relevant with the observational data. And that model is Finch and SKEA stellar model. Okay, in 1989, Maharaj and Martens gave an isotropic model, and Finch and SKEA have basically studied. They gave us a static spherically symmetric anisotropic distribution. Okay, and for this anisotropic distribution in 2013, work has been carried out by Ratanpal and Sharma. And here what I have done is I have done the extension of the work of this Sharma and Ratanpal. And finally we tried to check out with these well-known pulsars like 4U 18, 20, 30 or PSRJ 1903 plus 327 and so on. Okay, these are very well-known compact stars or pulsars where we applied our computations and we tried to verify whether we have produced a good working mathematical model or not, which is called physically viable model. Okay, so we basically started with the same expression, that was equation number 6. Now I had just changed this equation number by 31. Okay, what about 32? The Finch and SKEA have basically gave this part 1 plus r square by r square only. Okay, so Sharma and Ratanpal have worked with this 1 plus r square over r square in anisotropy. Okay, in 1989, Finch and SKEA have made basically this expression and studied the isotropic part. But in 2013, Sharma and Ratanpal have worked with this expression only 1 plus r square over R square. Okay. I don't know why it's not working. Anyway, so 1 plus R square over R square. Okay. Now, in my research, I basically tried to generalize this power, and then let us see what basically happen when we are considering the most general power n. Obviously, this n is nothing but a dimensionless parameter, and R is the curvature parameter. Okay. So once I have made the computation, I need to first of all cross check whether I am correct or not. And for that, we put here n is equal to 1. Once I am putting n is equal to 1, I will be getting the actual computation or the expressions by Sharma and Ratanpal. Okay. So as you can see here, these expressions, either these expressions or 24, 25, 26. Okay. You can solve these expressions and you can find the density part. So 8 pi rho is equal to this. When I consider 1 plus R square by R square to the power n, simplify it, I will get the expression of density to be equal to this, equation number 33. Similarly, the mass is connected with this relation, and radial pressure will be in this form. Okay, now coming to this part, basically I have 3 equations and 4 unknowns. Okay, and that is the reason that I need to take into account some assumption here, and that assumption is 35, equation number 35. First of all, this radial pressure must have some criteria which must be satisfied in order to assume such relationships. Okay, so this is not a blind relationship that we can take into account or assume, but this should be satisfied with some of the basic requirements. So if those requirements are satisfied, then we are through. Otherwise, we need to change this assumption. Okay, just after a few minutes, I will show you those requirements as well. But once I consider that expression, and then I can solve the system of equations in order to find this e to the power nu, which is a very large expression here. And the anisotropic expression is also obtained here. We developed the larger expression here. A1, A2, A3, and A4 expressions are nothing but this one. So basically, you just club these all 4 expressions in order to get the actual anisotropy expression, equation number 37. Okay, so it was a lengthy expression, and hence I am just writing in this way. Okay, now, okay, let me just again remind you that once you substitute here n is equal to 1, it should match with the expressions by Sharma and Ratanpal in 2013. Okay, and that was matching. Okay, now we know that this relationship 8 pi p per is equal to 8 pi pr minus 8 pi root 3a. So anisotropy should vanish when we consider at center, I mean r equal to 0. Okay, the anisotropy will be at the boundary because pr and p per, we are just trying to check that relationship. Okay, now we have few more parameters here, though, as I just told you that we have 4 parameters here, C, P0, R, and N, okay, which can be fixed by the appropriate boundary conditions discussed in the following slides. So, okay. Now, what is the boundary condition here? Actually, whatever the interior metric that we are trying to work with, it should match with the exterior metric smoothly. Smoothly in the sense that at R is equal to R, this, I mean at the boundary, Schwarzschild interior metric or whatever the new interior metric that we have covered or considered, that should match. Okay, so there will be a smooth matching from interior to exterior. And that is the reason that now I am writing in this equation number 39, that is Schwarzschild exterior metric, and I'm comparing it with the metric that I obtained, that is equation number 31. 31 is this one. Okay, so this 31 metric with this assumption. So this is nothing but generalized FINCH SKEA assumption. Okay, and now it should match smoothly with Schwarzschild extremometry. But when it will match, when you have this relationship, R is equal to 2 raised to n plus 1 m upon 2 raised to n minus 1. This is a simple relationship that we can obtain on the basis of this matching condition. Okay, one more thing. Now we have two components basically for this matching because these are identical. So first and second term. So out of this one, from the second one I obtained this one, and from the first term I am obtaining the value of this C. What is this C? Capital C. Capital C was here. You can see here equation number 36. When I compare this relationship, I must have the value of that integrating constant in simple language. So that value is nothing but this one. So basically, if you are in a position to calculate, you can calculate directly. If you are not in a position, you can have a continuous integral expression. Just you can see here in equation number 41. Okay. And this basically here, capital M is nothing but the total mass enclosed within a radius, capital R. So this equation 14 clearly shows that the compactness of the stellar configuration M by R will depend on this parameter N, which was not the case in the model developed by Sharma and Rattanpal because it was a particular case. But ours is a general case, and therefore now we need to justify this value of N. We need to identify that in which region we will get a realistic solution, or you can say a stable stellar model, and in which region it is not. Okay, now coming to the seventh part, that is, what are the bounds on such model parameters? Now, these are very standard requirements in order to establish your physically acceptable stellar model. Okay, so condition number 1 basically gives you non-negativity of density, radial, and transverse pressure. Similarly, condition number 2, it's a strong energy condition, rho minus PR minus 2p per. Condition number 3, that is d rho by dr. These are gradient conditions, and this should be less than 0. And condition 4, it's hydrostatic, sound speed square, that is dpr by d rho. It should be in between 0 to 1, and similarly dp per by d rho, it should be in 0 to 1. So due to the mathematical complexity of such expressions, it is really difficult to show analytically that all these conditions are satisfied. And there you need to now use any good mathematical software in order to visualize this thing. You can have a good plot here so that you can have an analysis or judgment that these entities, or these conditions are satisfied. Either they are non-negative, you can say it should be greater than or equal to 0, or maybe it has some bound like 0 to 1 here. Okay, so we have for this reason and with this requirement, I have now focused on this n part. Okay, so the power 1 plus r square over r square raised to n, that n has now some bound based upon this requirement. Now you can see here that PR and P perf should be non-negative at r is equal to r, that is at boundary. Once I impose these conditions, I can have this conditional inequality, that is P naught must be less than or equal to this, equation number 42. Okay, let me again explain this thing. You are now imposing these conditions on the solution that you obtain, on the matrix you obtain, like that the component of that matrix is given by this 40 and 41. Okay, 40 and 41. So you will have a very long interior metric, newly created metric on the basis of anisotropic fluid distributions. And now for that metric, once you impose these conditions, what you will get is you will have gradually all these conditions to be satisfied. So on the basis of PR and P perf, which is non-negative, you will have this equation number 42. Similarly, strong energy condition will give you another condition, another criteria by 43. You can see here the change of sign. Like here, this is less than or equal to, this is greater than or equal to. Okay, and therefore this less than or equal to P naught, less than or equal to this. Okay, one more thing. Now you have this condition as well, dp perf by dr at boundary r equal to r, it should be less than 0. So this condition, once you impose on your expressions, you will have another expression, P naught greater than this condition. Now see, You have found equation number 43. You have found equation number 44 as well. Still, we don't know what is the relationship between these two RHS, the right hand side part. Okay, it may happen that this part is greater than this one or the other way around. So once again, it's I mean, good exam of us that how we can find this I mean the smallest interval of this P naught. Okay, I moved further here for dp per by d rho expression, which should be less than 1. Again, our standard requirement, and which gives me this equation number 45, which is the right hand side expression. Similarly, other condition dp per by d rho less than 1 and dp per by d rho less than 1 at boundary and at center. These two will give me these two expressions, 46 and 47. Okay. Finally, I clearly try to check whether what are these conditions. I mean, what will be the narrowed down or the smallest interval of this P naught. And equation 42, which basically suggests us the lower bound and upper bound of P naught. Okay. Okay, one more thing. Now, one stringent condition on the stability of the system given by L. Herrera in 1992, which basically suggests that you have epsilon pub square minus epsilon r square is basically a potential stability. This is nothing but our difference of dp per by d rho minus dp r by d rho. So if you consider this difference, then it should be less than 0. Okay, in the throughout distribution, okay, fluid distribution. So once you use that expression, you will have another conditions here by 49 and 50. Okay, so now we are imposing another condition here, and then we found that this is the most smallest number on the right hand side part, okay, which is given by equation number 51. Okay, so now you can see that for this particular region, for equation number 51, if I try to draw the graph, that graph is giving me this value. So you can see here how nicely this region fits. Okay, the lower side is n, the y-axis is p naught, and p naught and n will give you the feasibility of your solutions only in this region. So if you cross this region, you will have no value, which gives you a stable stellar configuration. And that is the reason that you could also find the highest, or you can say upper bound of this parameter n, which was dimensionless and we considered earlier. So I found here n less than or equal to 4 by root 3, and if you go beyond this power, you will never get any stable stellar configuration. So you can say that how we started with the standard metric, and then we found out the analogous anisotropic solutions, and then we tried to implement all those requirements in order to find the stable stellar model. And once we imposed those conditions, we basically found out a very fruitful output, that is the upper bound of n. Okay, obviously lower bound was greater than 0, but the upper bound is 4 by root 3. So in this range, if you consider any value of n, you will surely get a stable stellar configuration. Okay, now what is the justification behind this, that I have found out the stable stellar configuration? It's clearly in front of your eyes. Like these are the stars that we considered earlier. Okay, and now I can set this value n, and for all these stars, if you see, you can have these values 0.3399, 0.3703, and like this. So these are the values for which I could find the relevant central pressure value as well, 0.1211, similarly 0.12, and so on. Okay, and now this is the observed mass and observed radius. Now see, this study has been extensively studied, and it is published in monthly notices of Royal Astronomical Society by Gangopadhyay et al. Okay, so they basically observed such pulsars with this value, with this much radius and this much mass. And now on the basis of this, you can say that in our calculation, when I put n is equal to 0.6154, I can exactly get that mass m 1.58 and r, that is radius 9.1 kilometer. So I could match with the actual values of those stars with our theoretical calculation. That is one part. Another part is, even without observing that star, with our calculation, we can give the value exact, or you can say approximate value of central density, surface density, the compactification parameter, and the dpr by d rho value. I mean, you can now discuss the density and pressures extensively on the basis of our calculations. Okay, so we carried out our mathematical model, and without even prior knowledge of this density or radial pressures, we can give our own value, and basically they are matching with the observed pulsars. In this way, in fact, even if you go beyond the list of these pulsars, you can always give the idea of the central and surface densities as well as pressures. Okay, and hence that was really a good thing that we started with anisotropic stellar configurations. Okay, now these are the some of the graphs that you can see here. Variation of density against radial parameters. Similarly, variation of radial and transverse pressures against the radial parameter. This is anisotropy, dpr by d rho and dp per by d rho. Strong energy condition is also satisfied. All these values on the left hand side or on the y-axis are in MeV per Fermi cube. Okay, and this is the relationship between PR and rho, that is the equation of state. Okay, these are some of the references, and here I stop. Any doubts? Any query?
Thank you, sir, for this wonderful session. Like,
My
it was
pleasure.
really great interacting with you, and like you explained everything, like these complex topics in quite simple terms.
Yeah.
Sir, I had a doubt.
Okay.
Like you explained the anisotropic tensor.
Okay.
And I wanted to ask that what is the like physical application? Like what does the each of the terms in the tensor represent for the pulsars and other bodies?
No, you cannot say that. For example, let me show you the expression first. Okay, are you talking about this one? Equation number 8?
Yes, this one.
Okay, now basically this gives you the relationship between matter and energy of a body, or you can say considered space-time. For example, you are talking about star. Okay, any celestial body you are considering, you first of all need to fix up the geometry on that body. Okay, and the metric. Once you consider a metric potential, at that time it will be connected with the energy momentum tensor. So name itself suggests that it gives you an idea of energy of that particular body and the momentum. Okay, so you cannot say that physically, say for example, this is the star, and for these points we will have this energy momentum. But as a whole, once you establish or once you implement the geometry on the basis of space-time metric, you will have different expressions of relevant energy momentum tensors. So it's something like we are getting any general point. Okay, xyzt, for example, in space-time diagram. For that particular point, you can always calculate relevant energy momentum tensor. Are you getting my point?
Yes, sir.
Okay, so in that way, these expressions hold.
Okay, I see. So you were also explaining that there are some 4 conditions that like there are some conditions that one need to satisfy for this
Yes, yes,
like
yes.
position. Like you said, you will be explaining it.
Yes, yes. These are the conditions. Just a minute. This is the list. primarily whatever the metric you are creating, that metric should satisfy all these conditions. In fact, the list is exhaustive. I have just considered here fundamental conditions which are required. But for the considered metric and for your calculation part, if any of these condition is getting violated, then definitely that stellar model is not stable, physically not viable. And in fact, in research, if you see, there are more than 100, around 129 models were existed even during 90s. And at that time, Gokru and Mehra, they have extensively studied all these models, because at that time it was not, I mean, established criteria that these conditions should be fulfilled in order to get physically viable model. So they have created a large table, and out of those 129 or around 116 models, only 9 models were there which were basically satisfying few, I mean, these requirements for the physical viability condition. And out of those 9, in fact, 5 were very prompt to give us an actual idea, or you can say a good configuration. And that is the reason, in fact, that we started with one of those 5 top metric. That one of the metric was this FINCH scheme metric. And that is the reason that we could extend the idea of FINCH and SKEA flawlessly, because that model was very strong.
Okay, so sir, like based on what you have said, like following the required mathematical procedure,
Yeah,
and the theoretical foundations,
yeah,
like we can construct any metric which can satisfy these properties,
yes,
and
yes,
propose that as a, you know, a viable solution which can explain the, like the orbits and the, like orbits of pulsars and the mass like you have computed. So like there isn't really a specific answer that we can give, because one might be able to calculate another metric tensor which can give this value. So like we have 2 answers for one problem. So we can't, how can we be sure that, okay, like this is the tensor that explains,
no,
like
no,
for relativity?
I got your point. But in fact, if you have multiple metrics, then both will satisfy your requirement. Okay, so you can go with either of the way. I mean, for some of the metrics, you will have a very simple calculation. For other metrics, you will have a very complex situation. Okay, so out of this, you can choose based upon your requirement, whatever the simplest metric you want to go with. For example, let me give you an idea that some of the interesting metrics are called, you can say, Einstein's cluster. Einstein cluster basically made up of the assumption that when you have no radial pressure, that is PR equal to 0. Now, this is really mind-blowing that when you consider radial pressure, which is almost 0, which kind of object it would be. And still it is really nice, and many of the researchers, they are in fact studying this vastly, and they made up with the a very good conclusion of the anisotropic solution, anisotropic analog of those isotropic equations.
That is quite fascinating, sir.
Yes, yes, yes. Okay, one question I can see in the chat box, that is by Thomas. Okay, e raised to nu is e, yeah, of course this e is nothing but an exponential function, right? Yes. Any more questions? Okay, thank you.
Thank you for the wonderful session, sir.
My pleasure.
Hi, so Vikrant here.
Hello, Vikrant.
Yeah, it was a really great talk. Thank you very much for taking out the time for this. And I'm sure you know that the participants here and the ones who have been to this talk will go back and read a bit more about tensors and the stress energy tensor and their implications and everything. So yes, on behalf of Nakshatra, I would like to thank you for this talk, and I will again reach out to you regarding the project in the near future.
Sure, sure.
Thank you, sir.
Thank you.
I think it's a good place to stop. Thank you for your time and have a
Okay.
good night. Thank
Good
you,
night.
everyone.
Good night. Bye.
Thank you.